Hi everyone. So in the previous video we looked into macroscopic balances of mass and momentum, and we said that these are important when you work on a control volume. You want to know the information, for instance, the mass flow at the boundaries, the forces acting on the wall, and so then you actually do your analysis on a control volume. On the other hand, if you're interested in the local distribution of velocity, pressure, and other variables for a fluid of interest, then you have to work with differential equations and work, in other words, with the microscopic, with the NI balances. And so this is what we want to do in this video. We want to look at the continuity equation, which is nothing but the differential conservation equation for mass. Okay, so to do that, we use the common approach of looking at an infinitesimal cube of dimension dx, dy, dz. So this is a dx, this is a dz, and this is a dy. And of course, the mass change that we will have in this infinitesimal volume can be related to the fluxes that we might have across the surfaces of this cube, which are of course along the x direction, the y direction, and also the z direction. Okay, so what we have to do is to translate into equations a very simple, let's say, conservation law, which is the rate of change of the mass in dV will equal the mass entering dV minus the mass leaving dV. Okay, so this is very simple. It's a very simple balance, and this is what we actually have to satisfy and to translate into equation. So let's start to express the variation of mass inside this volume. Okay, so the mass variation in dV. So to express that, we basically have to express a dm over dt. M is the product of rho times v. In this case, we know that the volume is a dx, dy, dz, so it's a dv. And so our dm over dt will be a d over dt rho dx dy dz. Okay, and so we're using the partial derivative because of course the density might be also non-homogeneous inside the control volume. So this is our expression for the rate of change of the mass. This is the rate of change of mass inside the volume. Okay, great. So now what we have to do is to have a look at the mass flow rates across the surfaces. Okay, so to answer to the question, let's consider first direction x. We have the dx with the fluxes going through the surfaces which are located at x here, and x plus dx there. Okay, so what we have to do basically is that we have to subtract the mass flow rate evaluated in x minus the mass flow rate evaluated at x plus dx. And you have to remember, of course, that the mass flow rate is expressed in general as rho, a component of velocity, which in this case is u. We call u the velocity in the x direction times the section. Okay, so how do we express then these two terms? Well, so let's express this. Let's continue developing this. So we have a rho times v, times u, just said, times dy dz. This is all evaluated in x minus the same quantity rho u dy dz evaluated in x plus dx. Okay, so of course what we can do here, you see already where I'm going, where I'm heading, is that we can develop in a Taylor series the flux that we have at coordinate x plus dx. So that this difference will be then provided by rho u dy dz minus, so we have a rho u plus d rho u over dx times dx dy dz. Okay, so by expecting this equation, we see that we have this term that will be possible to cancel out. And so in the end, our difference between the fluxes entering in x and the flux leaving in x plus dx will be simply given by, so m x minus m x plus dx will be simply given by minus d rho u over dx dy dz dx. Okay, so this is the expression that we will use for the contribution of the fluxes in the x direction. Okay, very good. So you understand that we can do the same in the direction y and z. So for the direction y, what we will obtain is minus derivative with respect to y rho v dx dy dz. So v is the velocity component along along y, and for z we will have minus derivative with respect to z rho w dx dy dz, and w is the velocity component along z. Okay, so now we put everything together. So the variation of mass equal to the different flux contribution, and so what we get in the end is derivative of rho in time dx dy dz equal minus derivative of rho u with respect to x dx dy dz minus d rho v with respect to y dx dy dz plus minus d rho w with respect to z dx dy dz. Okay, of course you see that on all these on the right and left side you always have this term dx dy dz, which is your volume, and so you can simplify that and you finally get this expression for the continuity equation, which is derivative of rho with respect to time plus d rho u with respect to x plus d rho v with respect to y plus d rho w with respect to z equal 0. Okay, so we have derived our conservation law in differential form, which will be valid in each and every point of our fluid domain. Okay, now you see that this equation is written in this form. We want to see if there are alternative forms that we can use for this equation, which are more compact. And so to do that, we will introduce, or actually not introduce, but recall a series of mathematical tools that you already know probably. So one is the gradient one is the divergence, and then we'll talk about two different kinds of derivatives. So the gradient is the generalization of a derivative to functions of several variables. And so it shows the direction of the steepest slope for a point at a point in a three-dimensional space. So it's an operator from R to R cube. And so if you have a scalar, it's indicated by this nabla phi. So the scalar in this case is phi. And so this will be expressed as a derivative of phi with respect to the coordinate x times a unit vector e in the x direction plus d phi over dy, and then we have a unit vector j in the y direction, and then a d phi over dz times k. Okay, but this is something you probably already know very well, so I won't spend too much time on that. So this is the definition of the gradient. What is also very interesting to use in our case is the divergence. Now the divergence is a vector operator, so it's applied on a vector that produces a scalar. So it's an operation in this case from r cubed to r. Okay, and this will actually tell you if the flow has the tendency to converge or to diverge from a source. Okay, and so if you consider a vector field, typically you will consider the velocity field. So the divergence is indicated by this nabla dot, and so this will be the summed the sum of these partial derivatives of the three components of velocities in the three directions. So it will be dvx over with respect to x plus derivative of vy with respect to y plus derivative of vz with respect to z. As we said, this will give you the idea of the tendency of the flow to converge or diverge. So if it's a positive, so you have a tendency to diverge from a point, as you see here. If it's otherwise negative, then it will indicate the tendency to converge. Okay, so like I try to indicate with this here. Okay, very good. So these are two concepts that will be useful in the following. What else can we introduce? Something that we already used now, it's the partial derivative. This is useful when you have indeed a function of many variables and you just want to consider the variation with respect to one variable. So imagine that you have a field phi, which is a function of time, but also space. Then, of course, if you take the partial derivative in time, it means that you are, in fact, holding constant all the other variables x, y, and z, and this is indicated by the subscript that you put out of these parentheses. Okay, and then we are going to introduce something that we will use a lot in this course. It's called the material derivative. It's also called substantial derivative, or even total derivative. And so the concept of this material derivative is very much related to the different views that you have of problems when you adopt a Lagrangian perspective or a Eulerian perspective. So imagine that you're doing experiment in a river. You want to measure the concentration of a pollutant. One approach to do that is, of course, to stand up on a bridge, for instance, on the river, and then measure with your device the concentration of that pollutant. But one other approach is that of being being inside the river, so moving with the river and measuring the pollutant as you move inside the river, because you are let's say moving in a solidar way, so, let's say at the same time as the river. So you're sitting in a boat in that case. The boat will move because of the uh, let's say of the movement of the flow inside the river, and so you will actually measure a concentration that will not only vary in time but only in space, because you are moving in the river. So the first perspective, so you on a bridge measuring the concentration of the pollutant, is an approach that we called Eulerian. You're standing still and you're just measuring the variation in time, although this concentration, of course, has also a variation in space. In the other case, you on a boat, uh, you not only consider the variation of this property in time, but also the variation associated to the motion, to the fact that you are not at a fixed position. And so this can be expressed in what we call the material derivative. So imagine that you have, and this is indicated with this capital D, and the way this is expressed is by using the chain rule. So you know that this is a function which is not only a function of time but also space, because you are moving on the boat. And so what you have to do is to say, okay, I have a partial derivative of phi with respect to time, but I also have a partial derivative with respect to x, and I know that x is changing in time. I know a partial derivative with respect to y, and I know that y is changing in time, plus the partial derivative with respect to z, and I know that z is changing in time. Okay, so I not only have the contribution of the rate change in time, but also the change associated to the movement of the boat, or in general to the fact that we are considering the variation in time of a quantity which is moving with a certain velocity. And so the certain velocity uh, with which this property is moving is indeed given by this component here, because you see that this is a velocity in the x direction, this is a velocity in the y direction, this is a velocity in the z direction. Sometimes are indicated, as we did before, as u, v, w. So the derivative, the material derivative, is the time rate of change of any quantity for a portion of material. So the quantity here is phi, but it can be temperature, the concentration of your pollutant, whatever you want. So the rate of change of any quantity in a portion of material that is moving with a certain velocity. So you don't only have the change in time, you also have the change associated to the movement of the flow. Okay. Okay, so this can be, for what you just said, we can actually rewrite this as d phi over dt. It's equal to what? So partial derivative in time plus d phi over dx dx, d phi over dy times vy, d phi over dz vz. Okay, but maybe you have already recognized by doing this development that we can express this derivative in a more compact way if we use one of the operators that we have introduced before. In particular, you see, if you look at these terms here, so we have Vx times d phi over dx, and then you have Vy d phi over dy, and then we have vz d phi over dz. You can actually see that this is the scalar product of the velocity vector and the gradient of phi. So if you see this 3 contribution here, this is the gradient of phi, and this contribution here, this is the velocity vector. Okay, so I can rewrite everything here as the material derivative of phi, okay, it's equal to the partial derivative of phi in time plus the scalar product of the velocity vector and the gradient of phi. So you see that you have a very compact representation now of the material derivative. Now let's go, so we have introduced basically the material derivative, the gradient of phi, the divergence of a vector, so the velocity vector, and the partial derivative, which is also already here. So how can we use all this information to, let's say, process and rewrite in a compact form the continuity equation? First of all, let's rewrite the continuity equation as we obtained it before. So this was the continuity equation that we found before, and so it was a d rho over dt, and then it was plus d rho u dx plus d rho v y plus d rho w z equal to 0. So something that I see now very clearly is that if I look at these three terms, this is nothing but the three terms that compose the divergence of rho times the velocity vector v. Okay, and so by realizing that, I see that I can simply write the continuity equation as d rho, derivative of rho with respect to t, so the partial derivative, plus the divergence of rho v equals 0. Okay, so the divergence of this product, which is, of course, you see there is a vector inside, will be a scalar, and so you see that this is also a scalar equation, as you would have expected. It's a scalar equation. But we can actually go a little bit farther, because what I can do is that I can develop all the terms in this continuity equation. So what I mean is that I can, looking at these terms, I can derive with respect to rho and then with respect to u, and then I get additional terms. So let's do that. What I can do here is that, so this is my original equation. So what I can do here, of course, is that I can further develop the terms d rho u, rho v, and rho w. And so I get d rho over dt plus u d rho over x plus v d rho over y plus w d rho over z. And then I do the terms with rho, so I have rho times du over dx plus du over dy plus dv over dy plus dw over dz equal 0. Excellent. So now I realize that I have two groups. I did it on purpose to separate it in this group here, and let's use another color here, this group here. Okay, so now if you go back to the definition of the uh, of the material derivative. You remember that this was something like d phi over dt equal partial derivative of phi over dt plus the product of the velocity vector, the scalar product of the velocity vector times the gradient of the scalar itself. And so you see that this is exactly what we have up here. Okay, so this first term is nothing but the total derivative of density. Okay, so it's d rho over dt. Now what about this second term? It's quite simple. So if you remember the divergence, you remember that the divergence of v was indeed the sum of derivative of u with respect to x plus derivative of v with respect to y plus derivative of w with respect to z. Okay, so what you have here is exactly the divergence of v times the density rho. And so we get in this way an alternative let's say formulation of the continuity equation. So basically in the end we can summarize that we found the following formulation of the continuity equation. By simply considering the fluxes, we get the formulation which is all explicit: d rho over dt plus d rho u over dx plus d rho v over dy plus d rho w over dz equals 0. By considering the definition of divergence of rho v, so divergence of rho v, we get the formulation d rho over dt partial derivative plus divergence of rho v equals 0. And by using the definition of the material derivative and divergence, so material derivative, of course, of rho. So let's change this. And divergence of v, we get the final expression, so d rho over dt plus rho divergence of v equals 0. In all these cases, of course, we get a scalar equation, which is normal. We have the conservation of mass. And my purpose here was just to show you that, of course, you can use the classic approach of an infinitesimal volume to derive your conservation equation. I just wanted to show you a little bit further that by using appropriate mathematical tools and definitions, in this case the divergence, the gradient, the material derivative, then you can get much more compact representation of the same equations. And so this is very important for the reminder when we will work in the next video on the Navier-Stokes equation. So the conservation of momentum in differential form. Okay, see you next time.